Hello, my name is Chris Barton, and I'll be going through my data analysis project for programming machine learning apps at DePaul. I used the Yelp academic data set for my data analysis project. This data set contained about 2.7 million reviews for about 90,000 different businesses in the UK, Germany, Canada, and US. Because of the size of this data set, I decided to perform sampling in order to get some of the classification algorithms to run on my computer. For that, I decided to use stratified sampling and only look at locations in the United States. So here I have some bash commands to just look at the data set, look at the lines, look at the size, look at the first couple lines. Here we can see the JSON object of the review data set and the business data set. Then I move on to using Python to actually perform the sampling. Here is when I ran into my first little hiccup. Because these are manually entered addresses, they're not guaranteed to be accurate or consistent. So to compensate for this, I used a function called Levenshtein distance, which looks at two input words and then calculates the edit distance you would need to take to correct one word and make it into the other. So here between hello and hello, we see that there are two edits needing to be made to correct the second word. So for this, I looked at all the correct spellings of the cities I wanted to sample, and if the Levenshtein distance was within a certain percent of the correct spelling, I considered it a matched. After which I randomly sampled all of the geographical regions I wanted to look at. Next up is exploratory data analysis. So here I'm just really looking to get a feel for the data and test out some of the intuitions I have about it. So here just looking at the data frame. Here's an interesting graph that shows the distribution of ratings throughout the data set. So here we see that 4 and 5 stars are given more often than 3, 2, and 1, which is somewhat counterintuitive if you buy into the logic that people only give reviews when they've had a bad experience. Additionally, this information will be important when I balance my data set for training the classification algorithms. And here we see some more graphs about the distribution of the number of reviews per user and business. Yelp also has a vote function where users can vote if a review is cool, funny, or useful. You can see the distribution here. And then moving down, after just kind of initially looking, I wanted to test out to see if any of my intuitions about some of the features that might be correlated with ratings are correct. So here we see the count of reviews per average rating. So here that we can see that there's not a strong correlation between the number of reviews a business has and their average rating, but there is a slight positive correlation. Here's the distribution of the length of reviews, and then the distribution of length of reviews per rating. So we see that there's no significant difference really between the length and the types of ratings. Next, going into a little bit more natural language processing type stuff, I see here a frequency, a word frequency chart. We see if we look at these words, there's really nothing too informative in here. However, once we move restop words, we start to see some pretty informative words like food, good, great, like. Moving on, I wanted to see if some strong adjectives were associated with higher reviews. Here we can see that likes is associated with more 5 and 4 star reviews and lower stars. And then for bad, it doesn't look like we had that same strong correlation. Next up, we used to move to feature engineering and modeling. Here I tested out 4 different classification algorithms and 2 different feature engineering techniques. Term frequency versus IDF frequency, unigrams versus bigrams. For modeling, I use naive Bayes, stochastic gradient descent, near centroid, and decision trees. So here I'm just kind of preparing the data set, balancing it, checking everything, getting some of my graphical functions ready, and testing it on multinomial Bayes. And then here a little bit lower is when I really get into the meat of kind of the analysis where I use Skylearn's pipeline grid search with various feature engineering techniques and parameter tunings. For multinomial Bayes, I just used feature engineering as there wasn't really many parameters I could use in that I could input multinomial Bayes. And then I loop through various sizes of the data set. So at the end, I get a graph like this that shows me at each size of the data set what is the accuracy of each one of the permutations of the various grid search. So here that we can see as we increase the size of the data set, the classifier does improve overall validation accuracy, and that even the various tweakings that we can do as we increase the size don't seem to matter as much than at a smaller size. Additionally, in this graph, we can see the runtime of it in seconds. So 10% of the sample only took 40 seconds, and then at the full data set, only 140. So that was really quick, actually. Next, I moved on to stochastic gradient descent. So here I tested out the feature engineering and then hinge log, perceptron, L2, L1, and elastic net. I'm just going to skip over to the results as we're getting crunched on time. Here we can see that it does increase in general. However, the variance seems to get quite, much more spread out as we increase the size of the data set, which is, kind of not what we saw in multinomial Bayes. Additionally, when we look at the time, we see it get, exponentially faster the larger we get. And here we're looking at 41 minutes at 2,500 seconds. Here we see the graph for the near centroid classifier. Again, so not as strong as naive Bayes as we see an overall increase. Additionally, you'll notice 36 and 33, so this one's actually pretty weak compared to the previous two. However, its runtime isn't really too bad, which is a positive aspect of it. And then finally, I use a decision tree, and here I have some more parameters such as the GINA and entropy class or splitter, and then 10, 5, 10, and 20 for the max depth. And here we see it generally does get more accurate as we increase the size of the data set. Here we kind of see two different groups break off. I suspect that this group is getting overfit as we increase the max depth and we train it on more data. However, this one was also significantly slower. It was in par with stochastic gradient descent, around a little over 41 minutes for the full training data. And then we come to the final graph, which is comparing each of the classifiers, so the decision tree, near centroid, stochastic gradient descent, and multinomial Bayes. You can see here that Bayes is the best classifier, pretty much right on par with stochastic gradient descent. However, the standard deviation of it is much smaller. There's much less room for error. So based off of all that, so naive Bayes has the quickest time as well. There's not a lot of parameters to tune, which could be viewed as a good or a bad thing. It's less likely to, it's less work, I guess, for the data scientist doing the job. So based off of the runtime of it, the overall accuracy, and then no need to really do like extensive parameter tuning, rated overall the best. So now I'll move on to testing it on the test data set. And here we can see the confusion matrix, which then, kind of actually brings up an interesting point, is that this really isn't a straight classification task, as these rankings are ordinal. So we can still look at overall accuracy as a good guide, but we might also want to commute some more regression-esque type metrics. So for this one, I chose to look at the mean absolute deviation. We can see is about 1.5 here for the test data on multinomial Bayes. Now, in conclusion, I think we can say that multinomial Bayes is, kind of the most efficient for this task at hand on this data set. Also interesting to see how the training size of the data can affect the accuracy and the runtime. These are really important considerations in any sort of business application, as data is not always cheap and it's not always abundantful. So in some cases, if you can increase the the size of your training data, it might be worth paying whatever extra money you have to do in order to get that extra accuracy. So that basically wraps it up. Thank you for taking the time to watch.